We present on the error analysis of 3D Gaussian splatting and an optimal projection strategy. Recently, 3D Gaussian splatting has demonstrated notable advancements in rendering performance by departing from MLPs and volume rendering, opting instead for Gaussian primitives and projection. The initial step in 3D Gaussian involves an affine transformation of this Gaussian function from the world space to the camera space via a viewing transformation matrix W. Subsequently, these 3D Gaussians are projected onto the image plane, i.e. z=1 plane, via a projection function phi. Unfortunately, Gaussian functions are closed under affine transformations but not under projection transformations. Therefore, 3D Gaussian splatting uses a Jacobian matrix of phi for first-order Taylor approximation, i.e. local affine approximation. The error introduced by the local affine approximation can be characterized by the Taylor remainder term. Clearly, this Taylor remainder term is a 3D vector. By computing the square of the Frobenius norm of this vector, we can obtain the function with respect to the random variable x prime. Finally, the error function with respect to the mu prime can be obtained by calculating the expectation of this random variable. In order to facilitate calculation, we might as well convert Cartesian coordinates to polar coordinates to solve the expectation. We depict the graph of the error function under two distinct domains. The error function is concave, with its minimum value occurring at the origin. Additionally, it can be observed from the left image that the minimum value of the error function is greater than 0, due to the fact that Gaussian functions are not closed under projection transformations. The right image shows that in the majority of the region close to the origin, the function values vary very gently. However, as the independent variable of the function approaches the boundaries, the function values increase rapidly, resulting in a substantial difference between the maximum and minimum values. Therefore, the naive projection of all Gaussians onto the same plane z=1 in 3D Gaussian may lead to larger projection errors for Gaussians farther from the plane center, which causes artifacts. Based on the analysis of the error function, we propose optimal Gaussian splatting. The first step, similar to the original 3D Gaussian splatting, involves transforming world coordinates into the camera coordinate system. Subsequently, instead of projecting Gaussians onto the same z=1 plane, each Gaussian is radially projected onto corresponding tangent planes. This ensures that the projections of all Gaussian means coincide with the center of the projection plane so that the approximation error is minimized. After projection, colors of points on the unit sphere are computed by alpha blending the 2D Gaussians on the tangent plane. Specifically, for a pixel on the image, i.e., u, v, similar to NeRF, we cast a ray. However, unlike NeRF, we do not involve the extensive sampling of points along the ray, which would significantly degrade performance. Instead, our focus is solely on determining which tangent plane Gaussians the ray intersects on the unit sphere. Then query the function values of these Gaussians for alpha blending to obtain the color. To validate the effectiveness of the optimal Gaussian splatting derived from theoretical error analysis, we conduct a series of experiments. For our qualitative experiments, our method is capable of generating more realistic details with fewer artifacts compared to other methods. We derive the projection error function with respect to image coordinates and focal length through the coordinate transformation between image coordinates and polar coordinates and depict this function. The peak of projection error mainly occurs at the image edges under a long focal length, resulting in artifacts at the image edges. As the focal length decreases, the field of view expands, leading to more Gaussians deviating from the projection center and an overall increase in projection error. Our method exhibits greater robustness across various focal length settings, mitigating the artifacts introduced by projection in the original 3D Gaussian splatting. For MEP splatting and scaffold Gaussian still employ conventional projection of 3D Gaussian, errors remain larger compared to ours. Since we combine ray casting and rasterization, we can adapt to various camera models by modifying the transformation matrix like NeRF. Take fisheye cameras and panoramas as examples. After training with the pinhole model, the scene can be adapted to different camera models just by replacing the transformation matrix. We can also use non-pinhole images as inputs to train the scene, since the optimal projection proposed in our paper is differentiable. Please check our paper and website for more details. Thanks for watching.